Great. So I think that's fine. We can start now. So yeah, thanks for coming to Ioan's lectures 3 and lecture 4. Okay, Ioan, it's over to you.
Okay. Hello, everyone. Welcome back. I'll try to today actually prove this theorem that I announced yesterday. We're a bit later than, we're a bit short on time because it took longer than I expected to do these things. But we'll see, we'll adapt. Maybe I'll skip something later on. But I think it's nice to see this kind of theorem because it's quite fundamental. So I remind you, we are at the self-dual point of FK percolation in 2D. And what I claim is there are two types of behavior at this point. One is kind of RSW type behavior. And importantly here, it's RSW type behavior even in adverse boundary conditions. So even if you have here dual boundary conditions on the side of the box, you still manage with positive probability to construct such a primal circuit. And the same thing for the dual because the two models are the same. So this is type number 1, which we will call RSW. And behavior number 2 is essentially saying that phi 0 is different from phi 1, and phi 0 behaves like a subcritical measure, meaning connections in phi 0 have exponentially decaying probabilities, and similarly in phi 1 if you take dual connections. So this I'll just put phi 0 different from phi 1. Once you kind of know that this happens at the self-dual point, it turns out you can very easily prove, or relatively easily prove, that the self-dual point is the critical point, that the phase transition is sharp, and that it is continuous in the first case and discontinuous in the second case. So by continuous and discontinuous, I mean the probability of percolating has a jump in the second case and doesn't have a jump in the first. Okay. And when I mentioned that what we would like to look at is presumably the criticality and what is close to criticality, this only makes sense in this setting here, meaning in the RSW setting. And what we expect is, I drew here on purpose a domain where the top half, a square where the top half is wired boundary conditions and the bottom half is dual boundary conditions, free boundary conditions, which means wired for the dual model. And if you look at the interface between the primal and the dual configurations, which is something you can very clearly define, then you would see here a curve that is presumably going to converge to a continuous curve, namely an SLE kappa, and the kappa should be given by this form. But we're not going to go into that, but just to know what we expect. So this is the kind of thing that we would really be interested. This is the kind of thing that will have universality properties and so on. So this is an interesting limit. On the other side, we have a much more trivial model. It doesn't mean you can't say anything about it, but the things that you can say are the tools would be different. They will not depend on Q, what you see in the limit and so on. So anyway, I'm not going to go into this side too much, but if there are questions, I can say a bit more about it. Okay, so let's start the proof. And the first thing is you want to somehow collect as many statements as you can that do not depend on whether you're in one regime or the other. So you'd like to say things that will be true in both regimes and then use them to separate the two regimes. So one such statement is an RSW theorem, which is true both when you're in a discontinuous and a continuous phase transition. And for reasons that I will become clear later, the good setting to work in is a strip. So we're going to consider an infinite strip of some thickness. I don't know exactly. I'll just call it capital N. And then we're going to consider small n smaller than capital N. And we're going to wonder, in this strip, do I have a long crossing, a crossing of a rectangle that is centered? Here it has height n and length kn. And if you believe that sort of RSW occurs, you expect this to be of order C to the K. Okay, so this is what I'm going to prove now. And this is really a core ingredient in this sort of thing. And there are several, there are different proofs of this. I'll try to give you a proof that I think is the most streamlined and easiest. And we will start off by looking at the probability that oh, by the way, maybe I should mention this. We're at the self-dual point, which provides an input for this kind of RSW thing. We saw in Bernoulli percolation, the input is the crossing of a square has probability 1/2. So this is already an input, and the game is to kind of lengthen the crossings. This is more or less what you want to do. And there are many, many techniques to prove such RSW statements, but most of them do rely on the fact that the lattice is rotationally invariant, meaning invariant under rotations by pi over 2. So you still need this kind of invariance under turn. And here it is not. So maybe I should write this. Model not invariant under rotation. Because of these boundary conditions, because you're in a strip, and this turns out to be quite an important thing. However, we do have certain symmetries. We have symmetry with respect to horizontal reflection. We have horizontal translation invariance. And we have that if you reflect the model vertically and you pass to the dual, you go back to the original model. So there's a sort of self-duality, but with this kind of reflection. Okay, so this is just to say that we're in a bit of an area where things aren't as standard somehow. Okay, so let's look at the probability that you have a crossing, a horizontal crossing, of an n by m rectangle as a value of n. So let's look at this probability and let's draw a graph for it. So what you will notice is that this probability obviously starts off at 1. And then as m increases, it somehow decreases like this. And what is the opposite of this probability? Well, if you don't have a horizontal crossing, then it means you have a vertical dual crossing. Yeah. And this probability is equal actually to the probability of having a vertical crossing in red in the primal. This is just because the model is self-dual and flipping it vertically. So flipping it vertically and passing to the dual gets you back to the original model. So these probabilities are the same. And so one is 1 minus the other, so the other one does kind of something like this. And our goal will actually be to find two values of m, namely m and 2m, where both these graphs have positive probabilities. Both these graphs are non-zero somehow, uniformly positive probabilities. And ideally, you want m to be of order. So this is kind of the game. The idea is this probability, as you extend, the way I like to think about this is you look at this probability as you extend the rectangle, this probability will go from 1 to 0, and the whole thing is to prove that it doesn't drop very abruptly, that it takes a while to drop to 0. If you do this, you're done. Why are you done? Well, because you can, this means that both this rectangle and the rectangle twice longer are crossed with positive probability, the larger rectangle is crossed like this, and the shorter rectangle is crossed vertically with positive probability. And once you get this, you can combine these crossings using FKG, and you lengthen them. Okay. Okay, so this is going to be what I'm going to try to prove, and I'm going to define M or M of N as being the moment where this probability here drops under certain.
Just to say, on the bottom of the screen, the leftmost thing that you circled is not visible. It's blocked actually by you. Yeah, perfect. That's fine, yeah.
Right. So I'll just take the first value of M such that this probability here, the red graph, drops below 1/8. So this is supposed to be this value, which is not at all, this is not at all 1/8, but you'll allow me to kind of say that this is 1/8, okay? Actually, the M will be here and the 2M will be here, but it's all the same. It's just positive constants. Okay, so I'm going to define this as M. And the first thing is I'm going to show you that this graph here doesn't collapse to zero too fast. Doesn't collapse to zero before with M much smaller than N. It really, if M is much smaller than N, then you're really crossing the horizontal line, which seems very intuitive, right? You'd expect that this graph crosses 1/2. If you have the Bernoulli percolation intuition, you'd expect that this graph drops at 1/2 when you're exactly at M equals N. But this isn't necessarily the case. Okay, so let me prove to you that this value of M that I've chosen here, this value of M that I've chosen here is really larger than N/3. Okay, so this is the first step, showing that at least rectangles of N/3 you can cross with a reasonably high probability. So let's suppose that it's not, assume it's not. Sorry, then N/3. And so that means that crossing these things horizontally is very unlikely, so crossing them vertically is very likely. So for instance, you can do these two crossings of these rectangles. So I've drawn here 3 rectangles in a row. They form a square in total. You can cross them vertically with probability at least 7/8, which is greater than 1/2, for instance. Okay. By FKG, the two crossings occur together, and what you can do is, if the two crossings occur, you can just condition on the leftmost crossing of the left rectangle and the rightmost crossing of the right rectangle. And when you condition by these crossings, the only information you need to know is what happens in the blue regions. And so what you will do then is you will ask yourself, okay, what can you tell me, what's conditionally on what I've revealed up to now and on these crossings, what's the measure in this domain, in this simply connected domain? And what you notice is that this domain here is something like, and I will want to prove that, okay, so let me just maybe say what I want to prove or argue. I want to argue that there exists, with positive probability, a horizontal crossing from a horizontal line linking the left to the right. Why is that? Well, if you look at this domain and you think what's the worst that can happen in the rest of the space, due to FKG, the worst that can happen is to have all edges closed. And if that happens, this domain is going to look something like this, with wired boundary conditions on the sides and free boundary conditions on the top and bottom. And here, essentially, your crossing probability is 1/2. I've cheated a bit. It's not really 1/2, but okay. So conditionally on these two crossings, you get a horizontal crossing with probability 1/2, and you will notice that if you have here a horizontal crossing, then this guy here, this rectangle here, which is an n by 1 over by n over 3, is crossed horizontal. So I just proved that this rectangle here, under our assumption that mn is smaller than n over 3, this thing here occurs with probability at least 1/2, that is, if you condition on the sides, times 1/4, which is the probability of having the two vertical crossings. And you notice we reach basically a contradiction. So this proves to you that the assumption was false, and therefore that m is larger than n over 3. So at least thin rectangles you can cross horizontally. Okay? Now, what happens at this value of mn? May I go to the new slide? So what happens at this value of mn? I'm going to draw now some mn rectangles. So this is mn. So at this value, you can both cross horizontally with probability at least 1/8, and vertically with probability at least essentially 7/8. Because you've really taken the point of transition. So the value of crossing horizontally is exactly 1/8, okay, up to small corrections that may come from a single edge or the graph that these probabilities here, they can't decrease with k too quickly. They have some room to that. Okay, so this guys, this is your kind of square that you can cross both horizontally and vertically. And now the whole thing is, let's see that I can also cross a rectangle double the size. This is the thing that we want to prove. And so if you remember, I'll basically redo the proof of Bernoulli percolation, and we'll show you that that proof didn't require any vertical symmetry. So the first thing is, it did require some vertical symmetry. We said we can go above or below the half of the square, if you remember, and we tried to do these diagonal crossings. Okay, here you don't know that you can go above and below the half of the square, but what you can do is you can say, let me just take the height here, which is whatever it is. I'll just decide what the height is. That allows you to cross both from above and from below. Okay, there is a height where both crossings from above and below are possible. You just start this level at the very bottom, and you just move up till the two sides have equal probability of crossing to the left. So now I can cross both from above from here to the left side, and from here to the left side with probability 1/16, just a constant. Okay. So now I'll draw this line. I'll draw this level. Maybe let's try it in blue. I'll draw it in blue everywhere. And what I'll show you is, since I can cross this square here, both horizontally and vertically above and below the blue line, I can add here a vertical crossing. And what I've created by FKG, all of this occurs with constant probability. So what I've created here is, if you notice, I've created a sort of diagonal crossing, a crossing that goes from the top left section to the bottom right section. So let's just draw that. So that's what we care about. So we just proved that this kind of event occurs with positive probability. Okay, so with positive probability, I have this. With positive probability, I have something like this. I hope that I drew them well. To illustrate my point, let's like this. To make some weird stuff happening. And what I'll do now is, as before, I'll condition on the lowest such crossing of the left rectangle, the highest such crossing of the right rectangle. And I'll try to create a symmetric domain where I'll use symmetry and self-duality to connect these two red crossings and form a horizontal crossing over. So let me see if I can do this well. I'll try to draw it up. Something like this. Okay, these blue lines are not, they're just fictitious. Okay, they're just used to define a domain. So now I need to be careful about how you define this domain. I essentially want one border to be red entirely, so maybe I do this. My domain will be, let me see. I'll try it in black. Like this. No. Nope. Like this. I want to take probably what's the outermost. And here it would be something like this. Okay, not sure. I haven't looked at this in a while, but it's something like this. And you'll identify four petals, four parts of this domain, which are symmetric. This one. Yes, I did a mistake here. Okay, and now if I look in this domain, so it's the domain with these boundaries. What you'll notice is that it's not true that the whole domain is unexplored. It is explored. There are parts that are explored, namely here and here. But all of these parts are basically as if you conditioned that the edges to be open there. And so now you have positive probability of having a crossing, even if you didn't have these open parts here between the green and the red, between the two purple sides. So let's draw a crossing like this between the two purple sides, like this. And you notice that any crossing between the two purple sides, either it lands, I'm going to just zoom in so that we can see what better. Either it lands directly on a red, like so say it landed here, or it lands on the part that isn't red, but it does so by crossing a red. And so just by self-duality and using the idea that having a crossing between the green and one between a dual crossing between the green and the primal crossing between the reds is equal, you get that there exists a primal crossing between the reds with positive probability. Okay. I mean, I've tried to draw here a more very general setting. If the domain was really symmetric, you would be probably more convinced, and it's probably good to look at it like this. What happens here is that you're in a symmetric domain setting plus some positive conditioning, meaning some conditioning that some edges are open. So that only helps your event that you're looking at. Is there any question about this? Do you seem convinced? Yeah, nobody's objecting? Okay. So this is the core of the thing. So what have we proved now? Let's review. We proved that we had these events of positive probability on the left and on the right. I think the probability was at least 1 over, I don't know, 1,000 squared times to get these nice diagonal crossings. Then you add in the fact that you need to cross to connect the two. Then maybe there's a 1/2 happening. But the point is, with probability at least this constant, I managed to cross 2mn by n horizontal. So I managed to create this. And this is the key. Now, basically, we're done because you can, you remember I said this, but you can take these, you can draw as many boxes of this size like this. If you want to reach something like Kn, well, you need order K boxes. Maybe 3K boxes suffice, because you know that these boxes of size Mn times n, you know that Mn is at least n over 3. And then each box is crossed vertically with a constant probability. And each two adjacent boxes are crossed horizontally like this with a positive probability. And by applying FKG, you have all of these crossings with probability at least C1 to the K, C2 to the K, where C1 and C2 are some universal constants for the horizontal and vertical crossings, and you get a long crossing as you wished. Okay? So let's, you can take this as a black box if you wish. Let's see what we get out of it. And I think it's good to say that because of this, for instance, if you remember, we had the question: do we have circuits at the point of self-duality? Do we have this, right? And our dichotomy was between whether this kind of probability decays exponentially fast or not in free boundary conditions. So what happens if you put here wired boundary conditions? Well, if you put wired boundary conditions, meaning if the boundary conditions are helpful to you, these boundary conditions are better off than the strip. So what you can prove is clearly this is greater than C, with C independent of N. So you notice that at the self-dual point, crossings, if you give yourself the good boundary conditions, happen with no problem. The thing is, can you keep this up even when the boundary conditions are adverse to you, are the opposite? Somehow the strip acts as the halfway between free and wired boundary conditions. Okay. Okay, so we come to the dichotomy part. Here are our events that we're looking at. There are exactly these kind of circuit estimates in adverse boundary conditions. And for reasons that I don't want to go into, I took here not that the boundary conditions are at slightly larger distance from the circuit, but it doesn't really matter. There are a lot of small tricks to get these boundary conditions closer to you and so on. And I'm going to do a proof here, which is more direct than the proof that appeared in the original papers. And it's, I think, due to Piet, who's there. But I'm not sure if he also picked it up from somewhere. But he communicated it to me. And I think he implemented it for height functions. So we're just going to prove that this kind of sort of renormalization inequality. So this probability controls the probability, the same probability for much larger values of the index. So multiplying n by k, you get smaller than un to the k. That's what you should remember. And there are some constants here, but they're universal. Okay, this is the sort of thing that we're going to prove. Why is this what we want? It's because once you have this, you will notice that you immediately obtain a dichotomy between either all the UNs stay uniformly positive, so this would give you the RSW regime, or if one UN ever drops below a certain value, namely 1 over 2 Cn, then you get immediately this kind of exponential decay. Why? Well, just you notice that if UN is smaller than 1 over 2C, then UKN or CKN rather is smaller than, and you use the above, and you get 1/2 to the k, which is exponential in, it's an exponential in this number, right? The n here, that you use here, this n here, is a fixed number. If ever that happens for a single n, you fix that n and you apply this renormalization inequality. Okay, you don't get it really for all n, you get just for of the form ck n0, where n0 is this this value of n, but that suffices to get all that you want for phi 0 different from phi 1, and all these exponential decays in phi 0 and exponential decay for the dual in phi 1 and stuff. So really the key is this inequality here. Is this convincing? Okay, so let's do this inequality. And it's a very beautiful proof that that you have here. Okay, I'll just show you what it is. So there are many scales involved. I hope I get them right. So what you'll do is you'll start with an extremely large, you'll fix n and k. And you'll start with an extremely large box that is kn times a large constant, so maybe 100. And you will look at this with free boundary conditions. And we'll try to make things happen in this box and bound the probability of the events that I'm going to show you here. First, we're going to bound the probability from below, and then we're going to bound the probability from above. And that's going to give us the inequality. So the bounds from below is, first, I'm going to try to make a big circuit of wired inside these free boundary conditions. This might cost a lot or not, I don't know, but it costs at least UCKN, where C is this 100 or 100/4 or something. Right. Now, when I have these boundary conditions inside here, I can build easy to make wired circuits. It's relatively easy to make wired circuits, meaning it costs me wherever I put an annulus, I can build a wired circuit in it by just paying a constant. This is the result of this RSW that we proved earlier. So what I can do is here I can build k wired circuits that are distributed along the line, a little bit separated from each other for boxes of size n. I guess this should have been 2n. Yeah. Whatever. Size. Okay, I can build these, and this is just going to cost me some constant to the k, because these boundary conditions are helpful to me. So it's just cost me a constant to build each of them. These constants to the k I'm very willing to pay without any problem. Okay, so this picture has a probability of at least constant to the k times UCKN, this probability. And now we're going to do something very strange, which probably is shocking, but we're going to say, okay, so this picture as well has at least this probability. Okay, we're going to delete the outside circuit. It's just an intersection. I'm not doing anything that is not correct. I'm just saying, if I wanted to obtain these sort of things, one way was to obtain them like this, but maybe there are other ways, I don't know. At least what I know is that they occur with at least this probability. And so now my goal is to say, look, I have here, you can see where I'm heading, maybe. You have here k events like in UN. But obviously, they're not in adverse boundary conditions. They're not separated. So I'd like to separate them. I'd like to build little wired circuits around each of them. If I manage to do this, little free circuits around each of them. If I manage to do this, then I'd basically be done. So this is what I'm gonna now try to do. And this is done in 2 steps. Let me see if I can, yeah, start off here. So first step is I'm gonna try to build in the immediate strip above, I'm gonna try to build a long free connection like this from left to right. So I can't do this directly because here, if I look at this strip here, the RSW that I've proved before is not really applying here. Why? Because you see the wired boundary conditions that are induced by this. A priori, I can't control this. But the wired boundary conditions that may be induced by these things are very close to the strip, whereas the free boundary conditions here are very far from the strip. But what you can do is you can apply the strip estimate repeatedly. So first you cut off here the middle third. And you say, okay, that cost me 1 constant to create. Then you say, okay, now I do a strip slightly below here. That should overlap, actually. I want to put another dual crossing conditionally on the first dual crossing. This costs me constant squared, and so on. And it turns out you can push repeatedly these dual crossings up by paying an increasing amount of constants till you get them really close to the strip. And like this, you get this kind of picture, and the cost of these 2 dual crossings because of RSW strip the cost is at least, the probability is at least C to the K, some constant to the K, okay? I don't know if this is something you can easily live with, but it's really the right order of magnitude. Okay, and once you have this, you're not completely done, but you still want to isolate these circuits from one another. So what you now do is you want to build vertical dual crossings here. But this is quite easy because what you have here between these things, these domains here, you can get them to be a little bit elongated. So just by self-duality, you can build these crossings by paying again a constant for each of them. So by paying again a constant for each of these crossings, like this, you have this kind of picture. Is this acceptable? And now what you can do, if you're a little bit used to doing some exploration and so on, you can say, okay, well, each of these guys here is basically one of these circuits, which is surrounded by a dual circuit. So itself is as if it was in a free boundary condition. And you can formalize this by exploring, for instance, the bottommost horizontal crossing here that is in a strip, the topmost here, and then these ones you should explore in a certain way, but this can be done. And what you obtain, therefore, is that the probability above is anyway smaller than UN to the K. Because you have K of these guys here are UN probability. And this is the renormalization inequality that we were aiming. So maybe I can comment a bit on this. This kind of renormalization inequality. So what I said that Piet suggested was to directly work with this type of inequality rather than doing it for k equals 2, which is the more sort of standard way to do this. And when I say standard, I mean these sort of things are already appeared for Bernoulli percolation in 2 dimension, in any dimension. Actually, in the work of Keston in the mid-80s, where he worked with rectangles. And then there were increasingly more streamlined way of doing this. They can be used in the off-critical regime to prove that as soon as you have this sharp threshold, as soon as your circuit probabilities drop below a certain value, you have exponential decay, is what we saw when we looked at Bernoulli, and they can be proved they can be used in a number of other settings. So I think it's a nice thing to look at in this self-dual setting. And in this separation of these 2 critical behavior, it's the most delicate situation where you use this kind of renormalization technique. Okay, are there any questions about this? If not, how much time do I have, Trish? I think we're reaching the end.
So you have about 10 to 15 minutes.
Oh, okay. That's amazing. Thank you very much. Then I will try to move on from this dichotomy theorem and announce things that start being closer to our current research, which is, we're not there yet, but closer, which is to separate the 2 dichotomy regimes. So we can now, when this theorem was first proved in 2015, I think it was, the dichotomy that was saying you either are of a continuous type or of a discontinuous type, it wasn't known which regimes correspond to which values of Q correspond to which regimes. It was expected, but it wasn't known rigorously. And actually, I should have mentioned that the original paper, which is this one, the original paper that proved the dichotomy, actually that did prove this part. So it proved that the phase transition for Q between 1 and 4 is continuous. And then later in this paper, we proved the second part. And very soon there were also papers that proved both sides, namely Q larger than 4 here and Q between 1 and 4 here, through different means. Okay, so there are many ways of solving this dichotomy, but I think they all rely, if I'm not mistaken, maybe, they all rely maybe on the fact that there is a dichotomy. So this dichotomy, because as I said last time, it kind of separates the 2 regimes and leaves no middle ground. And so you need very little, you just need to show that you're not in one of the regimes to know that you're in the other. So it simplifies what you need to show to decide which of the regimes you're in. And this was used. The techniques are very different here in the original paper. Once they established the dichotomy, more or less along the lines of what I've shown you, they used some discrete holomorphicity to prove that, well, you have some observables, they can't decay too fast, so you prove that there's no exponential decay in adverse boundary conditions. And therefore, you decide that you're in the first case. In this Ray and Spinka paper that you've probably known, you've probably seen in the course of Trish, the way they prove it is by relating to the 6-vertex model, which is what we're going to do next. But using some symmetry that occurs there, or rather some dissymmetry that occurs there for Q larger than 4. In this paper of Piet and Alexander Glasman, what they do is they again work with the 6-vertex model, and they notice that there exists some representation which changes form when Q is below 4, and in Q below 4, because of some duality statements, you see that you're necessarily in the continuous phase transition. But I'm not going to do any of this. I'm going to focus on the technique of this paper, which is a beta ansatz computation. Which essentially computes certain quantities related to Fk, and uses those quantities to decide whether you're in the first or second of the cases. So for the rest of today, what I wanted to show you is how Fk is related to 6 vertex, and maybe just, I will not do the beta ansatz computation because they're very orthogonal to what we have here, but I'll show you what the result that is relevant is, and I'll show you maybe a bit of the ingredients. But are there any questions about this? So I should mention that maybe these beta ansatz computation, they allow you to prove both regimes. Here in this paper, we just proved this regime because the other one had been done before, but with this technique, you can prove both regimes very directly. I skip? Let's go. So the 6 vertex model. We're going to work on a torus here from now on. So it's a torus that has a width n, I think I called it, and a height m. They're the same in my picture, but it doesn't need to be. We're going to have this kind of square lattice on these things. Both are going to be even, by the way. And they're going to be taken large. But and the model is a model of orientation of edges. Each edge has an orientation, and a configuration is valid if any vertex has an equal number of incoming and outgoing edges. So 2 incoming, 2 outgoing edges. This is called the ice rule. And what we're going to do is we're going to separate the 6 types of vertices possible into 3 categories that are drawn here. And actually, it's only the last category that we're going to be interested in. We're going to weigh the configuration. So the whole thing is going to have a weight that is C to the number of vertices of this type. Okay. If you want to look at this, if you've never seen it before, I know it can seem completely arbitrary. Why do I group vertices like this? Well, these two are the second column is obtained from the first by just inverting all the arrows. So that's why I grouped them by 2 like this. And what makes this thing special, what makes these 2 vertices special is the fact that they have the opposite arrows are both incoming or both outgoing, which is not the case for the others. So they're really, like, if you need to remember this, remember if you have 2 incoming arrows like this or 2 incoming arrows like this, then you're in the C case, and otherwise you're in the case which has weight 1. And you will then notice that there are exactly two C types of vertices. And so you weigh a configuration like this. You can define the partition function, which is just the sum over all the weights of the configuration, and you can define a probabilistic model, which is called the 6 vertex model. It turns out that this model is not as kind of I mean, it splits up into submodels into sets of configurations, because due to the ice rule, if you look at and if you work on a torus, it's important. If you look at the number of up arrows on each row of your torus, so here we have 1, 2, 3, 4 up arrows, and you look at another row, you have 1, 2. It's the same ones. Let's take another row here. 1, 2, 3, 4 up arrows. You notice that the number of up arrows on each row is the same. So you have a preservation of the number of arrows in one direction vertically. And you can therefore split the partition function according to this number. So here I've split the partition function according to this number. And there's a reason to do this. This number, or at least the unbalance, corresponds to an increment of heights. There is a way to map the 6-vertex model onto heights, which we will see maybe tomorrow, later on today. And this K represents the excess of up arrows with respect to down arrows or to half, represents essentially the increment, height increment as you loop around the torus horizontally. And it's natural when you look at these kind of height models to look at height models with a slope. So where the height increment is proportional to n. And so what we're going to define is the free energy at slope alpha as being the free energy associated with this sort of partition function, where the k here is taken to be proportional to n with a factor of proportionality alpha. Okay, and what I mean by the free energy, I don't know if you're used to this, but the standard is the free energy is you take the partition function, you take the log, and you divide by the volume, and then you take the limit as volume tends to infinity. I've taken here the limit in the order m to infinity, then n to infinity, because this is what we want to do. But normally, I think you can take it in any way you want. I'm pretty certain you can take it with m and n tending to infinity as they wish, in whatever order. I hope I'm not mistaken about this, but I think so. Okay. So there are two claims here. First claim is that this free energy contains information about the 6-vertex, about the 6-vertex, but also about the FK model. And the second information is that we know how to say things about this free energy, not compute it, but say things. Trish, you tell me whenever I should really stop.
Maybe in like 5 minutes.
Okay. So let me tell you what is the relation. We're going to see the relation between the 6-vertex and FK, and I think we're going to stop there. So what's the relation between 6-vertex and FK? Well, first of all, draw the 6-vertex, draw the FK model on the same torus here, but on a turn lattice. What I mean, I'm just going to show you where the points are on the right side here. The points are in the middle of the faces. The vertices are in the middle of the faces. The even faces, or odd, whatever, are those of the primal lattice, and the other faces are those of the dual lattice. Okay, just so that you know a little bit how these graphs are drawn together. Okay, and I'm going to show you first how you get from one configuration to another, and then how the weights are impacted. So on the left, if you want to go in this direction, you have your FK configuration in red. You draw also the dual configuration in blue. And then what you do is you draw all the interfaces between the red and the blue. So the way you draw the interfaces is you go like this. You kind of have a ray of light, and it's mirrored by both the primal and dual edges. So when it reaches here, it goes down. It goes like this, like this, like this, like this, etc. if you start off here, it goes like this, like this, like this, like this, like this, etc. Okay? Because you're on a torus, these things eventually loop back to where they started. So you get some what's called a loop representation. And I think it's clear to everyone if you give yourself the loops, then you can rebuild the representation. So there's a bijection between the loop representation and the primal and dual configurations. Then you orient each of the loops in some direction. So this is not something that you do in a unique way. And once you've oriented, you obtain a 6-vertex configuration. You notice that you obtain a 6-vertex configuration, meaning you obey the ICE rule, because each vertex here, which is a vertex of the lattice like this, has 2 loops passing through it. And you notice that the 2 loops are either an incoming, have one incoming edge, one outgoing. So in total, it's going to have 2 incoming, 2 outgoing edges. Okay, this is not at all a bijection. It's not an injection. It's not it's anyway. It's not a function because you've chosen orientation at random, or you've chosen orientations, and as you go here, this is not injective. And this, if you go in the other direction, it's not injective. So it's not at all a bijection between configurations. So why isn't it injective? Well, maybe I can just very briefly tell you what happens when you go in this direction. As you go from here to here, you need to decide from this picture how you get to loops in this picture. And for vertices like this, which are all vertices except vertices of type C, there's just one way to split this vertex up into a loop. It's this way. Into two loops, it's this. There's no other way. However, for vertices that are of the type C, you will notice there are 2 ways of splitting this up into loops. You can either split it like this, or like this. And these 2 ways of splitting are gonna really make a difference. Okay, so I've described here why this is not injective and why this is a one-to-many map. Somehow it's not a function. Once you've done this, if you want to continue the road, it's easy. You just forget information. So it's you just have an injection from here on out. Okay. So actually, this is kind of your master model, is the one that has the most information. You go this way by forgetting certain information, and you go this way by forgetting certain information. And so let's look at the weights of the model on each of these pictures. So I'm not gonna try to rewrite the weight here. Because I'm going to write it in you're going to have to believe me. The weight of this of a configuration here is essentially square root of q to the number of loops. And this is because we've chosen the self-dual, we've fixed P as being the self-dual point. Okay? You just need to trust me on this. It's something that you can prove by hand. There's a constant here that depends on mn, which I'm not gonna really look into. It doesn't really matter from a probabilistic point of view, but it's essentially this. So, and you see it now. I mean, if you look at this, you see why the self-dual point is so special, because the weight here that depends on the number of loops in this kind of representation doesn't really look at which side is the primal and which side is the dual. So it's not surprising that you have something. Okay. if you accept this, I think the rest of the correspondence is going to go quite well. You're going to write Q as being e to the lambda plus e to the minus lambda. So you choose lambda such that you have this sort of inequality. So each loop, you can kind of see it as being e to the lambda plus e to the minus lambda, and you orient it in one direction or another. And therefore, you choose here or the weight of this kind of configuration is e to the lambda times the number of loops that wind in this direction plus e to the minus lambda times the number of loops that wind in this direction. And what you can notice this is times. So if you do this, you clearly here, if you sum all the weights of the loops, you clearly obtain the weights of the weight here of this type. And what you need to see here is you need to see this number as e to the minus lambda over 2 pi, lambda over 2 pi times total winding. Okay, this is how you're gonna look at the weight of this configuration here. And when you look at this this way of seeing things, you're basically breaking down something global, a way of computing the weight globally into a way of computing the weight locally. Because locally, you can tell what is the winding, right? Just by looking at each vertex, you can count the winding of all the loops at each vertex. And you'll notice that the winding for vertices of this type is 0. And for the vertices of this type, the winding is either plus pi or minus pi. And so when you factor this in, it's not at all surprising that as you map this model with these kind of weights, here, what you obtain is you obtain a winding 0, so weight 1 for vertices of this type, and weight that is the winding plus pi and the winding minus pi for vertices of this type. So here's the formula that you need to look at. C is e to the lambda over 2, which corresponds to a winding of pi, plus e to the minus lambda over 2, which corresponds to the winding of minus pi. And this, if you look at it, you have this. Okay. So this is the correspondence. The way I like to think about this is you have a model and the weight of over configurations here, and you map it left and right. This is the easiest way to see. Now, because it's not a duality, you don't obtain equality of probabilities, but you obtain, for instance, these kind of equalities of partition functions, of free energy, and of partition functions, up to some constants. And the constant, this part here is something that you can completely ignore. It comes from the fact that there are constants, normalization constants. But you essentially obtain an equality between free energies, or between partition functions, but I've cheated a bit. So where did I cheat? Because we're on a torus, this whole thing doesn't actually work perfectly. Not all loops have winding pi over, or 2 pi or minus 2 pi. Only the contractible loops do. So you need to take that into account, but the errors that you obtain are marginal. They are not going to influence on the free energy. And so maybe the last thing I want to say is, can you really find lambda like this? And the answer is, well, yes, but lambda is going to depend, the value of lambda is going to depend on whether Q is larger than 4 or Q is smaller than 4. So if Q is larger than 4, lambda is a real. If Q is smaller than 4, lambda is unfortunately a complex number. And so that makes, in both cases, this model and this model are probabilistic models. But when you're in this regime here, the model on loops is not a probabilistic model. So here, okay, and this kind of is a bit of a bad news for the correspondence because it shows you that it's not so easy to translate probabilities. You can't do inequalities so easily, but it's not that bad. And we'll see after the break how you can use this to still extract, translate information from this side to this side or from this side to this. Is that okay?
So let's, yeah, that's okay. Let's thank Ioan. Any questions? Maybe I have just two very quick ones. So Q equals 4 is also real, right? Lambda is real.
Yes, in that case, lambda is equal to 0, and it's very easy to understand. I mean, much easier to understand the correspondence. It's essentially you just orient the loops IID. It's the only one where you have such an easy interpretation.
Right. And in the proposition, you don't put the slope. Does that mean it's slope 0? For the
Here? No, this is for all. You're taking all slopes.
What's the slope of the FK? Wait,
It just means you don't. It just means you take all the configurations.
So what's F6V then? F6V is the sum over all.
Over all slopes, all configurations, really. And I'll show you afterwards how you can use the slope to refine this.
Any other questions? No, so let's thank Ioan again, and we see you at 2:15.
Bye-bye, thanks.